Hi. Well, if you're watching this DVD, that means that you went through the challenges of the first DVD covering units 1 through 7. Hopefully, you stopped it, you reviewed it, you got your system working out there. You're kind of feeling kind of good. We're now getting in the second DVD, and we're going to unit number 8, overcurrent protection of control conductors. This unit covers motor control circuits, how they're protected against hazards related to overheating in accordance with the National Electrical Code. You understand the fundamentals of theory, and that's why you're at this stage. Hopefully, you have some understanding of fundamentals of conductor sizing and overcurrent protection as it relates to the National Electrical Code. If not, if you finished our electrical theory course, that is covered in basic electrical theory, conductor sizing, overcurrent protection, and that just a little basic fundamentals having to do with that. So we're making an assumption. Do you understand what a breaker is, the time current curves, and differences between fuses, circuit breakers, one-time fuses, dual element fuses? If not, get that theory course, finish that course before you continue on, because now we're getting into some code. Let's get going. Protection of control conductors. Overcurrent protection is based on the size of the conductor. Larger conductors, larger protection. Smaller conductors, the smaller the protection and capacity needs to be. We can use control conductors as small as 18 gauge wire, and those references have to do with the National Electrical Code, 43072. .72, 725.23. This has to do with class 1 control circuits, and this has to do with motor control circuits. We're not going to get to that right now. To properly select overcurrent protection for a control circuit, distinguish whether the control circuit is a separate control circuit or whether it is a common control circuit. So let's kind of identify those two terms. First one is a separate control circuit. A separate control circuit, you can see right here, we're coming off the auxiliary contacts, getting our 3-wire control, 1, 2, 3, coming over here. Here's a neutral coming down, going to one side. Here is our overcurrent protection. So this is a separate, well, since we're providing a separate protection for these conductors, we have to size that protection based upon the ampacity rating of these conductors. Note 1 of table 43072, column A, requires a conductor sizes 14 and larger be protected based upon table 31016. If you're an electrician or if you have electrical background, you should be familiar with table 310.16 and how you size protection for conductors. Let's go ahead and jump to the code, and let's go to 437. That slide said what? 43072B, column A. We are in Article 430. Relates to motors, motor circuits, and controllers. We are going into Part 6 of Article 430, which is motor control circuits. We are in Section 430.72, overcurrent protection of motor control circuits. And we are now looking at, I'll get the heading in here, Table 430.72b. And there's a column A, which talks about separate protection provided. And let's go to a graphic right here. Separate protection provided. Well, when you have this scenario, then the code says, well, if you use 18 gauge wire, provide 7 amp protection. Well, you're not going to get a 7 amp breaker, but you can get a 7 amp fuse. Well, then you provide 7 amp fuse protection. So not likely for separate protection for that size, but you might do that. A 16 amp circuit or 16 gauge wire would be a 10 amp. And then note number 1 says, well, look, if it's larger than, or if it's 14 and larger, note number 1 says go to 310.15 as applicable. And when you go to 310.15, it basically tells you to go to table 310.16. What are the common size conductors that you guys use if it's not going to be at 18 or a 6? Now, Dan, yesterday, I think you said you use 18 and 16s quite a bit.
Yeah, we use 16 on most of our control circuits.
Now, do you have a separate overcurrent protection for the 16?
Yes, we do, because we have, most of our control is actually PLC, so we have separate by section of the
In the
equipment.
PLC, it has, now is there overcurrent protection in the PLC?
Well,
where
all outputs do.
all the outputs have overcurrent
They
protection.
have fuses because they're triac outputs and they want to protect the
So you use an
electronic
18
part of
gauge
them.
wire, 16 gauge wire,
16 gauge, yes.
and your PLCs have, the outputs are fused.
Yes.
And what size fuses are you actually using?
2 amp.
Okay, but you could go up to
You could go up to
10 amperes. Now, Eric, Dow Chemical, You guys don't use 16 gauge wire for controls.
Now, typically what we're going to do is all our starters are going to be pre-wired, and the only wiring that we run into is the external wiring.
And I'm talking about the control wiring. Are
Right.
you running separate overcurrent protection for separate control wires? Because that's
No,
a topic
because-
right now. That's
no.
a topic right now. So
Right.
we're not doing it. All right. So you are, but if you ran larger conductors, and if we went with this scenario where you have separate overcurrent protection for the control circuit, then you'd go to table 31016. Now, for you, Dan, that's pretty common because you're using PLCs, you're running separate protection, you get them down to 2 amperes running 16 gauge wire. Eric, you're not having separate overcurrent protection. Let's go to the second one. Common control circuits. A common control circuit isn't considered a branch circuit. Therefore, it has either supplementary protection devices, which would be like a fuse block, or the motor's protection device is used to protect the control circuit. Let's take a look at this here. Where we're making a connection and we're making a tap off of the circuit conductors themselves. Is that what you do a lot?
Yes, that's what we use.
All right, let's take a look at this example here. So this already pre-wired. Line 2 picks up one side of the coil, and then we pick off a line 1 with a 3-wire, in this case, our example, 3-wire control circuit. This one has no overcurrent protection. And if we go to table 43072B, column B, let's go to the code. Now we have to move over to column B. Column B says provided by, let me see if I can get a little bit closer here. Provided by the motor branch circuit protection. So column B says that, well, we can't see the wire size, so I'm going to have to kind of go back over here. But column B is conductors within the enclosure. Let's take a look at our graphic. These conductors, because of the shading, Mike's made it real clear that these conductors, the control conductors, are contained within that particular enclosure. So now, column B says protection provided by the motor branch circuit. Column B, conductors within the enclosure. And what size wires do you run, Eric?
Well, if they're
Control.
within the enclosure, they're by the manufacturer.
Ah, you know what? I'm glad you said that. If they're within the enclosure, the start-stop button is part of the controller, the assembly, column B applies, but since it's part of the enclosure, column B doesn't apply to us in the field because it's automatically done by the manufacturer. Can I do that with column B, guys? Can I cross out column B? Everybody accept that? All right. And we got 18, 16, and 14, so when I kind of move this over, let's go to conductors that extend beyond 18, 16, 14, etc. So let's see if we have a slide next. So that one is column B, done by the manufacturer. Overcurrent protection for a common control circuit is based on whether the control circuit stays within or extends beyond the motor control equipment enclosure. Let's take a look at that code. Remember that. You had it extending, which is going to be column C, and then within is column B. Now, column B, if it's within, we don't worry about it. If it extends, we do. In some cases, the branch circuit, short circuit, and ground fault protection device for the motor is permitted to protect the common control circuit. Now, I said this, or I implied this, but I really like to take a look at this graphic. What we're saying is this. You have a 100-amp breaker. You have 8-gauge wire. We have no overcurrent protection for these conductors. And there are cases where we then can allow us to use the branch circuit protection to protect these conductors, as long as these conductors have a given size. And that's where 43072 is. If you have 18-gauge wire, then you can, 18-gauge wire, then the manufacturer would be able to tap off of a controller circuit as long as this device didn't exceed how many amperes? If it was a column B, that was 18-gauge wire, what would it be?
25 amps.
So this would be maximum 25. And if they had a starter that had 16-gauge wire, well, then the maximum branch circuit that it could be connected to up here would be 40 amp. And 100 amp would be good for 14-gauge wire. But if we are extending it beyond, then you can see that it's 7, 10, 45, 60, and 90, which we'll talk about. So we can use the branch circuit protection device to serve as the protection of the control circuits, depending upon the size of the conductor and the size of the conductor relative to the size of the protection and whether or not the conductors leave the enclosure or whether they stay in the enclosure. We're not going to deal with staying in the enclosure. We're going to deal with when they extend beyond the enclosure. And that was the part about within the enclosure is column B. And we're not going to worry about the conditions of those numbers because we've already seen that here on table 43072B, dealing with the 18 gauge wire, 25 amps we just talked about, the 16 gauge wire, 40 amperes. Now, if the control conductors leave the motor control equipment enclosure and are routed to other equipment, then the motor branch circuit ground fault protection device cannot exceed the values given in column C. So let's take a look at that example. So 18, 16, 14, 12, 10. Got to move this baby over here. So if I'm going to be using 18 gauge wire, the maximum the branch circuit protection device could be for the motor, short circuit ground fault, is 7. 16 gauge wire is maximum 10. But if I then go to a 14 gauge wire, I could use 45 amp branch circuit protection for the motor. If I had a 12 gauge wire, I could use those conductors. So a 12 gauge wire is only good where the branch circuit short circuit protection does not exceed 60 amperes if I extend this out. Now, what size wire do you use, Eric, for your controls typically?
Well, Mike, I hasten to reiterate that this is for tapped control conductors that are directly off the branch circuit.
And I'm glad you brought that up. We're not talking about a fuse protection. We're just saying,
Right.
hey, listen, you're tapping off of control conductors, and there is no overcurrent protection for those tap conductors. You're using the branch circuit, short circuit, ground fault protection device to protect those
Right.
tap conductors. So therefore, there's a limitation on the tap conductors. Do you typically provide protection of your tap conductors?
Well, we don't have tap conductors per se because we have 480 volt motors and our control conductors come through a transformer. So it's a different section.
All right, so then right now we're not going to get involved in
Right.
what you're doing. Okay. So now we are making an extension away from it, but if I want to use 16 or 18 gauge control wire, and the tap that I'm making here is going to be exceeding the values given on this particular table. Let's say I want to use 16 and 18. Obviously, it's only 7 or 10. Then what I'm going to have to do, put a fuse block in there, provide overcurrent protection for those conductors. Dan, or any of you guys, is it common to make a tap and not have direct overcurrent protection for the control wires extending beyond the enclosure? Or is the practice, well, let's put it this way, hold that. If you're going to do that, you're pretty much limited to some pretty small circuits, right?
Right.
A 40 amp protection device, a 60 amp, that's for 14, 60 amp is going to be for 12. You're probably not going to be running 10 gauge control. So more than likely, in some very small circuits, you'd be able to make your connection, make a tap, and take off. Is that pretty much there? So, but if we're going to get larger than smaller circuits, you need to provide overcurrent protection for those conductors. Then we'd have to go with a fuse block and provide a protection. That's if it's no transformer involved. Let's take a look here. Fusing, all right? Here is fusing of the circuit, and we're making a connection to it. And the fusing would be on both phases if it's going to be a 240 volt or line to line. We're going to provide fuses back here. Since this is going to be line 1 and line 2, we're going to have a fuse for each of the phases. And if it's a 120 volt circuit, we just fuse one phase. Control transfer protection. Now, this is, Eric, where you have a lot of transformers. Now, let's talk about that. Control circuit transformers typically have a single phase, 2-wire primary, and a 2-wire secondary. Now, before I get into this, I'm making some assumptions. I'm assuming you understand what a 2-wire primary is and what a 2-wire secondary is. If not, I hate to do this. I'm not trying to sell you theory. I'm saying, you know, you really need theory. And one of the things I've learned, and I teach it, and I preach this, you want to do theory before you do any course of ours. I don't care what you do. You need to have the fundamentals of theory because it is used in every course. If you're taking a grounding and bonding class, I'm going to tell you, you need to go take the theory course. If you're going to go to a national electric code class I'm talking about, I'm going to tell you, you need to make sure you get an electrical theory class. If you're covering electrical calculations, I'm going to tell you, you need to complete the electrical theory class we have because it is the foundation of everything. You guys feel the same way about that? That you need to have those foundations. With not, you know, you're just struggling and things just don't seem to fit. And when you do have that fundamentals, it's like, I understand what that means and why that. Now I understand why the instructor was why it was so important to get those series circuits and parallel circuits and Ohm's law and all these crazy things. It seems like it makes no sense. It is absolutely critical. All right, so we assume you understand transformers, primaries and secondaries and common magnetic couplings and how the whole thing works. Here we go. Overcurrent protection is always required on the primary side of a transformer. Primary protection can be provided by the requirements of Table 450.3b. Now that reference is from the 430.72c2. Let's go to the code book, 430.72c2. Having to do with, let's go 72c. 72c is control circuit transformers. Then we go to number 2, compliance with Article 450, and it references 450.3. And when we go to 450.3, A is over 600 volts, which we're not dealing with, and B is 600 volts nominal or less, which we are, then there's a table that tells you how to provide protection for transformers. Let's go with method number 1. Overcurrent protection isn't required on the secondary side of a controlled transformer if the requirements of 430.72b exception 2 are met. Well, let's go back to 430.72b exception 2. Conductor supplied by the secondary side of a single-phase transformer having only a 2-wire single-phase secondary shall be permitted to be protected by overcurrent protection provided on the primary side. I'm not going to get into any more details than that. And that is this. Your primary overcurrent protection can be used to provide overcurrent protection for the secondary, as long as it's a 2-wire primary and it is a 2-wire, actually, as long as it's a 2-wire secondary is the only critical thing, without getting into the details as to why. 2-wire primary and a 2-wire secondary. And you can get into the code book, and it has to do with a ratio and how this is going to work out, which I think is beyond the scope right now, unless you guys think we should talk about that ratio. Okay, just simply that primary protection. Now, Eric, use our example. You get your 40, is it 40 to 120 that you're dropping down?
Yes.
Is the transfer part of the assembly?
Yes.
Is there fuses automatically built within the equipment?
There are.
And so really you're coming off of X1 and X2, 120 volt control circuit.
Correct.
So we don't have to get into all the sizing and all the details here because we want to understand that the secondary conductors are considered protected by the primary protection device. Do you have secondary protection or no in that?
We do have secondary protection, but by the same token, these are motor starters that are built by manufacturers, and so they're products.
Right. And
So-
we don't. Okay. All right. Let me see if I can give a summary here because this is like, what's going on? I like to distill this down to what do I need to know as an electrician? Just cut it all off. Here's the deal. If you have a motor circuit and the motor branch circuit short circuit protection device going to table 430.72 isn't beyond 60 amps, then you could make a tap off of the motor branch circuit conductors and you could use 12 gauge wire. Okay, I can say I got a circuit conductors right there. I can just tap off of my motor circuit control and 12 gauge wire and I'd be up to 60 amps. Hey, once you get past a 60 amp branch circuit short circuit protection device, well, now you're going to have overcurrent protection for those conductors, and there's a couple ways to do it. One, run a separate circuit, take it to the panel, get your own control wires, provide the overcurrent protection according to Table 310.16. Probably, what's the largest wire, Eric, that you guys are using? 12 on a
gauge.
general. All right. Well, if 12, but Dan, you're using 16 because you have the overcurrent protection set at 2, but it could have been up to 10.
Well, that's on the outputs. The inputs, we actually group them and put them on 10 amp.
Okay,
circuit breakers.
all right. But if I ran 12 gauge wire, put it on a 20 amp breaker, and then I can take off and do whatever I want to do. Or I can go ahead and make a connection by equipment that already had that has fuse blocks in it, and just put the overcurrent protection to provide it, or get a transformer, step down transformer assembly, and it's there. So as electricians, smaller circuits, 12 gauge wire, I'm going to be fine. If it's larger circuits, 12 gauge wire is going to be fine. I just have to make sure I provide the overcurrent protection of, let's say, a 20 amp protection device, and I'm set. Dennis, I know this was important that I cover this, and I don't want to blow it off anymore, and I don't want to, but is there anything you want to focus on making sure these guys understand about this part?
No, I mean, to me, this was kind of a key part because, if they're pulling the wire and they get this given to them as a project, they just start scratching their head and they're going, well, do I, like you said earlier, you got a 100 amp breaker, you're feeding the motor with number 8s. Do I pull number 8s to the start-stop station then? How do I size that?
In your application, do you typically have taps to the controls, to the branch circuit conductors?
Same thing that these guys here are dealing with. We're going to have a transformer in the MCC, and then it's
all right, transformer
pre-wired.
MCC, it's already taken care of by the manufacturer.
Yep.
We're cool. Go 12 gauge wire, you're good shape.
And
If
typically
you're
it's-
going to run your own control wire, then just put a separate overcurrent protection device of a 20 amp breaker, run 12 gauge wire, and you're going to be fine.
Correct.
Eric?
Mike, one of the reasons we run 12 gauge is simply for mechanical resiliency. Some of our motors are 600 to 1,000 feet from the motor control center, and so you have to pull that much wire, and it's just for mechanical sake.
And also voltage drop,
Right, voltage
which we're
drop
not
as
going to
well.
get into.
Right.
Good point. All right. Well, that's kind of okay, kind of a tough little unit there. Make sure you take a look at that in the textbook and review that. That's NEC stuff. Let's go to unit number 9. Indicator lights and illuminated push buttons. This unit covers the use of pilot lights and illuminated push buttons that indicate the status of a motor or associated equipment. All right, we got a pilot light. Basically a lamp, internal lamp. We know we can change the color of this lamp. Is that right, guys? You told me that yesterday. The push buttons, we can make it a red, a blue, a green, yellow, whatever we want to. So, there's, oh yeah, Steve has those little buttons right there. So we have that option there to kind of make that. And so,
You just change these lens out.
and here's just the symbols, right? And here are just the symbols that you can use. Here's just a green pilot light. Here's I guess a pilot light being supplied by a transformer, right? Reduced voltage, and I guess some have resistors and some kind of added safety features, which I don't care about right now. We just know that these are pilot lights, and they are different symbols, and they have different applications. Now, Dan, you told me about some pilot lights, some experiences in what you guys do with the pilot lights. So I think it's a good time to talk about that.
Well,
About-
the pilot lights that we generally use have the transformer type, and the bulbs that a lot of the transformers use are 6.3 volt.
Hold on.
So
So,
they're-
you get a 120 volt circuit going to, is that the one right there?
Yes, this
All
is
right, we'll
one
see if
right
you can
here.
zoom in that. That's a 120 volt circuit, and there's a transformer built into that specific pilot light that drops that voltage from 120 to what?
6.3 volt, or 6 volt
6 volts.
nominal. Yeah, you have the contacts down here. This part is actually the transformer
So you have a
part.
transformer. You have a 120 to 6 point. What the heck would you put a transformer to a stupid little pilot light?
What we do that for a lot is because if you use a normal incandescent bulb at 120 volt,
Okay, yeah, makes sense
and
to
that
me.
shorts or it burns out, the filament in there is likely to short circuit and really raise your current on
Hold
that.
on. You're saying
And
if you ran, hold on. I'm saying you're saying you got a 120 volt circuit. You got a light bulb. There's a short circuit, and we are on a controlled transformer, right? Or you're on a programmable controller in your particular case, right?
Yes.
So when it short circuits, the bulb burns out, it short circuits, now it draws a lot more current than it would have with the element being high resistive. What's the effect of that?
Well, since we use solid state outputs and are having fused at 2 amps, then you'll blow the fuse.
Oh, right.
And that's not a desirable effect. If you have it through the transformer,
Hold
though,
on.
you won't have that.
So if I blow the fuse, I'm blowing the fuse to the control circuit.
Yes.
So here I have a control circuit with a light bulb. The light bulb burns out. Now I drop out the whole assembly, whatever that whole process was, just simply because of a failure of a light bulb.
Yes, that can happen.
So by having a transformer, if the light bulb, okay, what happens if the light bulb shorts out the transformer?
You don't get that much current on the 120 volt side of it.
Oh,
It's only
because
the
we've
6.3
yeah,
volt.
yeah, because we've dropped down that energy. We dropped it down. Okay. All right, so now we know why they have light bulbs with this symbol right here. There's obviously a special application that people have solved the problem that they had with that. Connecting light bulbs for full voltage. Most pilot lights operate at full voltage of the control circuit connected between line 1 and line 2. Just, if you push this button here and you're on line 1, right there, it gets 120 volts and it works. I'm just trying to show you how a light bulb works. It's, not a big deal there. Yeah, let's say application here. All right, I got line 1, I got line 2. I have voltage on this side all the way to this side. So I have voltage on one side of the coil. I have voltage on one side of the light. I have, probably should shade this. I have voltage up to here, through the stop button. Voltage stops over here, and this is normally open, so that's it. All right, let's see what happens. If I press the start button right here, I like this better. If I press the start button, I get voltage to the coil. I energize the coil. It closes its associated contacts, which is the M contacts, the holding contacts, interlocking contacts, the latching contacts, the securing contacts, whatever you want to call this. It's closing the main contacts that we're not seeing to the motor, right? The motor runs. And because this auxiliary contact right here is being held closed by the M coil by pressing the start button. Okay, here's the voltages. Okay, here's the voltages. Okay, if I press this button, okay, it was pressed, it's energized, it's closed, it now remains energized. So now the light shows green. And basically, if you put your lights in parallel with your coil, then when the coil is energized, since the light is in parallel with the coil, it will receive the same voltage, right? Laws of parallel. Then, in this case, we're using a green light saying, yes, the motor's running. Hey, lights, do they use lights? Is there certain colors that use lights? Does green mean it's safe? Let me see. Green is safe. No, green means the motor's running. Red means it's not safe. No, red means the motor's... I'm missing something there. I'm confused.
I think we're all missing something, Mike, because in our case, red means danger, the motor's running. Green means it's okay, the motor's stopped.
Okay, so what color should this be? Is this the wrong color in this graphic? What is it standard practice in the field?
It depends on the engineer or the architect. Yeah. It really does.
Really?
And the client. Yeah, it really does.
So it could be green one time saying the motor's running.
It could be green saying the motor's running. It could be green saying that the control circuit is energized.
And it could be red saying that the motor's running.
Exactly.
Because it's danger.
I just hope that the same people who do the electrical stuff don't start doing traffic lights.
You know what's cool with traffic lights? They use what? A red wire for the red light? A green wire for the green light, a yellow wire for the yellow light. Those guys got it together. They must say, listen, we don't want anything to do with you electrical color coding guys and your lights configurations. All right, at least I know I'm not crazy about the lights here. So it could be any color you want to. It's up to the designer how you're going to do it. And I guess different people feel different ways. And they feel different ways at different days. One day it's a green, one day it's a red. All right, we'll move on. All right, let's take a look at this one here. All right, here is our... Here's our points. Okay, let's see. Here's one comes in to the stop. Okay, one comes into the stop, and that's closed. Okay, that's closed. And then it goes over to a start. So from stop to start, okay, start is open. Okay, that's open. We don't see the auxiliary contacts here. And then from start, it goes over to the coil, which we're not seeing. That's going to be over there. But then this one goes to the green light. So this green light is going to be in parallel. And, of course, here's the indicating contacts right here as well. So you have to play with this. I'm going to be honest with you. Even everything we're covering, and I told you yesterday, hey, listen, I'm not a motor control guy here. I'm just a facilitator here. I'm as confused as probably most of you guys watching this DVD. What I'm talking about, I'm confused. I'd have to take this, and Eric, you said it yesterday, I'd have to get a continuity meter. I'd have to, and Dan, like you said, you need practice here. I need to be able to draw this out. I need to be able to see the button. I need to get to the contactor. I need to mess with this thing a little bit. And it just takes me a couple times I got it. And then I might have to make little notes for myself so that if I had to go back to it again, I could see that. So those of you that are watching this, please feel comfortable that when you sit down for the first time that you're going to be uncomfortable and I got to just take some time And you know, as I was thinking about this as electricians and as myself as an electrician, I have a tendency to overstate my experience when I was an electrician so that I could get a little bit more money and I could get the next job. And I got fired because I couldn't hook up a 2-stage thermostat after 4 hours. You know, you're placed sometimes in a situation under a lot of pressure. So even though you finish this course, if you're going to get into some kind of control circuit, you need to have a little quiet time. You need to be able to just look at this, get the components, and if somebody tries to intimidate you, you know, you're going to have to just take the baloney from the guys and just say, hey, listen, you must be a brilliant guy, you understand this, but you know what? I'm still working on this. I'm still trying to learn. I mean, if you don't want to give me a break, that's okay, but I just need a little bit of quiet time. So give yourself a little bit of a break that you're going to have experience. This is not something you can just look at here without getting to it. All right, let's go on here. All right, what do we got here? All right. I like this diagram better. Okay, I got to stop, start. Okay, press the start button, energize coil, close and hold the contacts, keeps that energized. Oh, 1 second, hold on. Right now, my red light is on. The way the circuit is drawn, because it's shown a de-energized state, the red light is on, indicating that there is power, I guess is what they want to say. And then if I press the start button, energize the coil, close the M contacts that were open the M contacts that were closed, now the red light goes off. So let me see the logic there.
So the red would indicate stop.
Okay, red indicates stop. And when you press the button, the light goes off, indicates either the motor's running or the bulb is burnt out.
Or power failure.
Oh, power failure. There you go. Hey, is the motor running? Yep. Well, how come we got no power in the building? Well, the bulb's out. Motor must be running. Isn't it right? I mean, so I'm not quite sure if that's the best design to indicate whether the motor is running or not, but whatever. We'll go with what we got here. All right, what do we got here? Oh, here we go. Here's that picture again. All right. We can see voltage to the light. Red light is on. Press the start button. It closes the M contacts that were open, the auxiliary contacts, and then we had what? Auxiliary contacts that were closed, the 4 and 5. That'll get open. Light goes off. Indicates motor's running. We're in good shape. I love that design. That's a great one. All right. And where do you locate the pilot light? Of course. Oh, let's see the wiring. The wiring of the pilot light is going to be coming from the contactor, going back to the contactor in parallel to the M coil. So right here, I'd run how many wires up here? Just 2 wires. And it doesn't matter if this is a quarter mile away. It's just 2 wires to turn on that light. It gets in parallel with the coil. So the key here is get in parallel with the coil. Don't ever make a critical determination that a motor is running or not running based only on the status of the pilot light or illuminated push button. And we just saw that one example that's like, okay, the bulb is not on, indicates the motor is running, there's no power to the building, or there's no power to the circuit. You know, is that good enough information for you? Can you make a decision off of that information? So right there you can see, and I'm sure we can come up with another scenario, well, motor is not running, but in reality the bulb is out, the motor is running.
Well, even to go one step further, you could have absolutely no control power whatsoever, and your contacts could be welded shut.
Oh yeah, let's talk
And
about that.
so-
Hold on, say that. You say it because it's just intuitive to you.
Right, well, let's say a motor's running, and you go to turn the motor off.
Okay.
Well, if the contacts of the contactor have been welded shut
Now the contacts is what get brought in when you energize your coil.
for the brand, right?
You energize the coil, wham! It brings it in and makes the contacts. And you're saying, okay, you turn it off, but the contacts don't release because they're welded shut.
Right.
Why would contacts weld shut?
Well, if you've got a lot of arcing, you could have some metal actually fusing and welding together.
So is that, I won't say common, but is that common?
It happens enough times that you better be careful.
In other words, all it takes is one time to get killed. That's how common it had to be.
Exactly.
In other words, if it welds shut, you press the stop button, but the contacts are still closed. But hold on. But if that were the case, using this previous example, if I press the start button, I energize the coil, right? I now close the contacts. The motor is running. I press the stop button. I de-energize the coil. The light then comes back on, right? Indicating the motor has stopped, but in reality, the motor is still running.
That can happen, yes.
You guys, right? And that's a danger that we're saying. You got to be careful. You can't depend on lights to tell you whether something is operating or not operating. But I guess we could use other controls, and that's where you could put something for centrifugal, voltage. Is there any voltage physically at the motor? Is there any current being drawn by the motor? Is it moving fluids? Is there something happening? You can actually tell, yes, that motor is energized or de-energized. Or is there no fail-safe? You need to go there, turn it off, lock it, tag it, then open it up with the proper protective equipment and find out whether it's off.
Exactly.
There's no other way, and even that people get killed on.
Right.
Okay. All right. I am done with the push buttons and the lights, rather. And we're moving on to Unit 10. Selector switches and truth tables. A selector switch is rotated by hand or key rather than being pushed and have 2 or 3 possible positions. I got a little one right here. Here is my push button. Press it down. Here's a push button, press it down. That's not a selector switch. Here's one that says one position, here's another position, and there's another. So there's a selector. You can select the type of switch condition that you want to go to. And here's another one down at the bottom here. So you have the push button, then you have the selector switch that's going to change conditions. That's what we're talking about right now. Truth tables. Truth tables or target tables are used to indicate the functions performed by different selector switch settings. All right, this is a truth table. We'll talk about that in a second. But let's just take a look at this selector switch. Here are the symbols. There's an A, which shows in the J position or the K position. J, in this case, happens to be identified as jog. K happens to be identified, as run. I would think J would be jog, but we're not going to go there. Okay, J is run, K is jog. That the A1 contacts in the J position is closed. If you go into the K position, you turn the selector switch to the other, right here, take a look right here. So let's say that was in the J position, I turned it to the left. That's going to give me a set of conditions. Let's take a look at that. In the J position, A1 contacts are closed, A2 contacts are open. Then if I take the same exact switch and I go in the other direction, that's going to put us in the K position. That means that A1 contacts now will be open and the A2 contacts will be closed. Let's kind of put this together in an actual circuit. I love our 3-wire control circuit now. I feel comfortable. I'm not as tired as I was yesterday with them. All right. Let's say we are in the J position. And in the J position, it indicates that A1 is closed. We can visualize that. We can see that. So if I press the start button, I energize the M coil, which closes the M contacts, which then is going to lock the M coil in. Main contacts close. The overloads are not open. The motor runs. The main contacts are not being shown. Everybody with me there? So now, how do you stop this? Press the stop button, and then, of course, you have to start it again. That is in the run position. And that's what we just did. That was the run. I'm sorry. Here's the run. Run position, press the start button, energize. It keeps the contacts closed. So coil is energized. Let's go into the jog position. Well, in the jog position, the A2 contacts are closed, but the A1 contacts are open. Now, you take your start button, and when you press the start button, do I have a sequence here? If I press the start button, while I'm pressing the start button, I'm energizing the M coil, and the motor, of course, the contacts are being closed, but the moment that I release the start button, because I cannot maintain the interlock or the latching contact here because I've opened it because it's in the jog mode, this motor then could only run when I press the start button, but the moment I release it, then the motor stops. So you just kind of tap it. So you go to start, it closes the contacts, it goes in the A1 position close, press the start, it runs. You go into the jog mode, which was the different condition. You press the start button, it runs. You release it, it stops. So here you're able to take a switch and create 2 different conditions. Now let's see if we can take a look at the actual truth tables. Under the J position, A1 contacts are closed. J position, A1 contacts are closed. And that's a number 1. And what the number 1 means, it means true. Are these contacts closed? And the answer is yes. Or you could put a check mark there saying, well, the contacts are closed. Now, it doesn't have to be J and a K. It could be whatever. It could be a 1 and a 2, right? I mean, it could be whatever the selector switch is identified, and they'll give you a truth table with it so you know, okay, well, under this condition, these A1 contacts are closed. But if you go to the K position, well, then A1 contacts are not closed, but they're open, but the A2 contacts are closed. Now, we had some discussion about this in our break time, and Steve, I think you said something about the shelf life, or one of you guys talked about why we have a truth table.
Well, as far as a truth table, it helps you to determine which position that switch is going to be in and what kind of continuity you're going to have, because some of these can get a lot more complicated than the one that we're looking at here, where you can have a lot of different functions and so on. But that truth table comes from Boolean logic, which led into digital logic with your ones and zeros, one meaning on and zero off. In this context, maybe we just think of it as a switching chart. It might be a little bit easier to really assimilate that.
See, it doesn't come, it isn't like it's a normally closed contact, which is normally closed, and so there's your symbol, so it's a done deal. No, because it's not normally closed, it's not normally open. I mean, well, how did you set your switch? And then that affects how the other switches are going to react and how they're going to respond.
Yeah.
And how did you change it again? Well, if you change it again, well, now we have a different set of conditions. We got to know, okay, well, in this setting, what are the conditions of the switches? And I think, Dan, you were saying that these switches might have normally closed contact symbols shown on it. What were you saying about that?
Yeah, that was the point that I wanted to make, that the truth table will tell you which contact it is, but don't get confused with the normally open or normally closed,
That's shown on the physical device.
because that might just be the contact block that they had to use
Oh.
to get you to that position.
So they use a contact block, they put it together, that's already pre-assembled, that's a normally closed contact.
Yes,
But when they put it under a selector switch, depending upon how the switch setting is used, that normally closed contact under that setting might be open.
that's exactly right.
Or it
yes.
might be closed. So
Yes.
you can't be looking at contacts. You have to get with the truth table to find out in condition 1 or condition 2 or J or K or whatever manufacturer identification is, how is the setting going to be? And with that, then you're able to proceed forward.
And
Let's
the
go-
2 or 3 positions are pretty easy to learn, but they can be up to, 6, 7, 8 different selections, and that's when the truth tables really are needed.
Okay, and then
So
Eric.
the more complicated
So
they
as
get.
you were saying, different lengths. I mean, this thing.
Right, and also you also have on many of these switches 2 different sides. And so what'll happen is maybe you have one contact block white and a contact block red, or whatever the designations are. Well, J might have one function for one contact block, but a totally different function for the other one. And so if you're going to work with switches like this, really what you need to do is find some quiet place, some quiet time, sit down with your book and figure it all out and make it fit your application.
But I'm an electrician, so I always look at everything as an electrician. Aren't you going to give me this switch? I mean, am I supposed to figure out what switch I'm supposed to use? I mean, Dan, do you got to figure out what switch you're going to use to accomplish, or somebody's doing this design? Who needs to know about the selector switch? I mean, I'd just put a toggle switch on there and turn the stupid thing on. I would be done. I mean, I don't care. But maybe you want more than just the motor running all the time. Who is determining what the needs are in designing the circuitry and telling me, use this switch, because if you give me this switch and you tell me the colors of the wires and I understand what's going on, then I might have to go to the truth table or a continuity tester to figure out which one it's going to be, and I'll make determinations. Or am I supposed to know how that I need a selector switch? Who designs that?
Well, whoever designs the circuit is going to be the one that designs how many selections you need to be able to make.
Okay. So they're going to tell you what you need to use for that specific application. So Dennis, you're gonna as a contractor, you're buying this switch, you're putting those wires in there, and the guy's taking this switch here and he's gonna hook it up, but we need to make sure he knows how to hook it up.
Right.
He's not designing it. He's just simply, okay, you got a 4 selector in a 4 position, well then, 1 position, this is true false, this is making break contacts, okay, this one is this, so then you connect these wires here, boom, boom, boom. Okay.
Well, a lot of times that's the case, on new construction, you're going to have a print and a plan to work from, but a lot of times in the world for the small contractor, if you want to become the go-to guy, and
Yep,
become
I knew you were
distinguished
going to
in
go
your
there.
field.
I could see that
If
coming.
you're going to be the guy that wants to be in the phone book and they all look at, well, call Joe's Electric because he knows controls.
So he'll be able to hook up this press and this and this and
without the
this
plan,
machine
without
tool
the print, when
with-
they need it at midnight, that's the guy they're going to call.
All right, I can see where some guys love controls. I don't love controls, so I'm not the go-to guy. I'm going to say, call Steve Arnn. He'll take care of you. Let him have fun wasting time as far as I'm concerned. All right, and I can appreciate that where it's going to. All right, let's go on. 3 position selector switches. Oh my gosh. All right, here we go. Okay, we have a JK and an L. All right, but it could be a 1, 2, and a 3, or 13, 14, and 15 maybe, or something like that. All right, let's take a look at this. All right, K means it is no contacts. J means A contacts are closed. K is no contacts. L means contacts 2 are closed. So I'm going to see if I can figure this out. So J is A would be check. And A2 is open. No jack. K, nothing. Neither one of them are going to be closed. That means closed. That means open. That means open. That means open. L, that means open on the L position, but A2 is going to be closed. I think I got it. All right, let's see if we can put this in use. Here's application. All right. Okay, hand, auto, off. In the hand position, the pump runs. Why would they say hand? Does that make any sense? How about just on?
Some people will call that manual.
Why
That's
manual?
real common to be on a pump circuit, to have a hand-off auto. That way, for testing, you could turn the motor on.
Okay, so if this was called manual, it makes sense to me because it actually has hand-off auto. Manual means it's manually on,
Yeah.
right? I got that. And then it is off, which means there's no contacts being made, and then it's in the auto condition.
And in the auto position, you would probably use your float that you have pictured there.
So now, without getting in the circuit yet, if I'm in the hand
Hand-operated.
in the manual mode, I'm obviously getting power from line 1 to my coil.
Right.
I'm bypassing all the controls. That's a two-wire control circuits, right? That's the one
Yeah,
right there,
exactly.
right? When I go to off, I'm basically having a stop button that's open. It's now complete. There's no power going anywhere.
Right.
When I go to auto,
You bring in all your control devices.
now I'm bringing in from the line 1, I'm now going to my 3-wire control circuit.
On your float switch.
Well, you're
Or
going
my-
through float
Float
switches,
switch.
temperature
I'm sorry.
switches,
I'm
whatever.
going to whatever the
your
control
devices.
I determine it to be. So I could go to auto, but the motor might not start if it's a 3-wire control circuit,
Right.
which would require me then to go to the start button. And once I start it, it would run fine. But as soon as I lose power or I stop it, even in the auto mode, it's not going to automatically restart because it's a safety applications or whatever the other conditions were. I'm starting to get this stuff. I'm starting to like controls.
All right.
Yeah, that's what I'm talking about. I love controls. All right, let's go back to our graphic. All right. In the hand,